So for this problem, we are going to be using the curve analysis information that we have learned over the last week or two. So when you're solving these problems or you're given a function and then you're going to figure out like all of this different information, I recommend that you find f prime using the power rule, factor and graph, and then you're going to find f double prime, same thing, factor and graph. So I'm giving you the steps here, but in the future, I just want you to know that these are what the steps are. So let's find f prime. So using the power rule, easy enough. 3 times 1/6 is 1/2 x squared. 2 times negative 3/2 is negative 3x. And then derivative of 10 is 0. All right, so that is x times 1/2 x minus 3. So then I get x is equal to 0. And I'm sorry, I should set this equal to 0. So 0 is equal to x times 1/2 x minus 3. So I get x equals 0, and I get x equals add 3 divide by 2. I'm sorry, add 3 divide by 1/2, I get x equals 6. Another way you could have factored is you could have factored out a 1/2, and then you would have gotten x minus 6 in parentheses. So either way, the idea is where are the zeros located? So f prime, and I just do a sketch because I think you can make a t-chart. I'm sorry, not a t-chart, a sign chart, but I think that sketching is honestly the easiest way. That is just a personal preference. You are free to use a sign chart if you prefer. So I have zeros at 0 and 6. This is a parabola that faces upward, so I just need a sketch. It just looks something like that. Notice that you only need the x values and then the general shape. You don't need to know anything else. And then f double prime, I'll go ahead and do f double prime. That is going to be 2 times 1/2 is just 1, so 1x minus 3. And then this is just a line. It crosses the x-axis at x equals 3. It has a positive slope, so it looks like this for f double prime. All right, so where is f increasing? So f is increasing when f prime is positive. So that is going to be from negative infinity until we hit 0. So you'll notice that that is when f prime is above the x-axis. Likewise, f prime is above the x-axis from 6 to infinity. So that is where f is increasing because f prime is positive. Remember, f prime being positive means the slope of f is positive. If the slope of f is positive, then f is increasing. All right, where's f decreasing? So that's when f prime is negative. So that's between 0 and 6 because f prime is negative. F has critical points at x equals. So critical points are where f prime is equal to 0 or undefined, and that happens at 0 and 6 because f prime is equal to 0. F has a local maximum. So remember, a local maximum is when there is a change in slope. You have a maximum when your slope changes from a positive slope to a negative slope. Now, this is the slope function. So where does this graph change from positive to negative? And that's right here. That's where we have a change from f prime being positive numbers to negative numbers. So f has a local maximum at x equals 0 because f prime changes from positive to negative. All right, f has a local minimum. So minimum likewise occurs when you have a negative slope to a positive slope. So look at our slope function. Where does our slope function change from negative numbers to positive numbers? And that happens at x equals 6. Because f prime changes from negative to positive. Remember, equaling 0 is not enough. There needs to be the word change and be specific. Okay? If f prime changes from negative to positive, that means the slope of f changes from negative to positive, which is what creates a minimum. All right, now concavity and points of inflection are all about the second derivative. So f is concave up when f double prime is positive. So where's f double prime positive? Here. Okay, and remember, we're not talking about the slope of f double prime. We're not talking about the concavity of f double prime. Where is f double prime? Positive numbers. That's where f is concave up. So f is concave up over 3 to infinity. Now, if you had used, I already kind of went over this. I had to stop the video because a kid came in. Okay. So if you'd used hard brackets here instead of soft brackets, that would actually be okay depending on the definition of it's hard to explain, but if in limit proofs of calculus, they will include these as hard brackets. Now, I'm okay with either one because on the AP test, they will specifically say open intervals. And when they say open intervals, you'll know that they want this. Okay, they'll say over what open intervals. So, however, concavity starts with a C. This is how you remember it. Concavity starts with a C. C's look like soft brackets. You never are allowed to use hard brackets for concavity. Never, ever, 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 ever. Concavity is always soft brackets. So it's only ever going to be open interval from 3 to infinity. And that, again, is because f double prime is positive. F is concave down when f double prime is negative. So that is from negative infinity to 3 because f double prime is negative. And then points of inflection occur when there is a change in concavity. So f has a point of inflection at x equals 3 because f double prime changes sign. And you could say from negative to positive, that's fine, but you actually don't have to. You can just say f double prime changes signs. For maxes and mins, you need to be specific, changes from positive to negative or negative to positive. But for points of inflection, because it works either way, it could be you have a point of inflection as long as f double prime changes signs. So that could be from positive to negative or negative to positive. If f double prime is changing signs, f has a point of inflection. So you don't have to be super specific about that.